All right, welcome back to another video. This is for the JNCIE-SP. I'm kind of looking around the room weird because I just saw a fruit fly. If you've been a long time follower of this channel, watching every minute, as I'm sure you have been. An update on my fly issue is that I do not have as big of an issue. I've just been spraying and taking care of every fly I see, and I've been seeing less and less over the next few days, and it was never a huge issue anyways. All right, so back to the JNCIE-SP. We're going to be working towards those goals from before, where we look into authentication for OSPF and ISIS. So where we left off, we were learning how to make service affecting configurations remotely without losing access. And I think, oh yeah, and there's just one device left for doing that, and that's router 1. Good news is we're going to be using a source address for router 1 that is already a direct route on router 1. So we won't need to use some special source address. We can just go right from the Ubuntu Docker guest. So it looks like I'm having that glitch where the CLI is gone. It's just presenting itself on the Docker guest so far. All right, so I'm going to need to just reboot that. It's really quick on the Linux machines, unless I accidentally had extra things selected. Nope, okay, so perfect. That won't take too long to reboot. All right, so I'm in. Oops, I failed to get a DHCP address. Oh, and I lost the one I had. So let's first and foremost do a history and add those back on. So it's going to be command 365. Oops, that actually looks like it's for deleting it. So we're definitely going to need command 371. So I'll start with that one. Oh, but we can't use that yet because we don't have the IP set up. Okay, so we're going to need command 203. All right, and now we can do command 371. Okay, so now it's accepted since we do have reachability to this network through the directly connected route applied to EF1 or interface ETH1. Yep, so that looks good. I'll do a route. That's good as well. Okay, so let's do a SSH. Okay, and we've got the public key authentication set up, so that'll overwrite TACX. All right, so let's configure this final router to have OSPF instead of ISIS. And we'll need to add additional interfaces for this since it's connected to the 2 host routes. So here's proof that I won't disconnect myself by deleting this. And that, sorry. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3. So let's see here. Oh, now see that's interesting because I actually would have expected myself to sever that connection because I have a connection to the loopback address on here. So oh, okay, yeah, but that's going to work because let's think about our routing tables here. So let's do a show route for the IP address being used as a source address in the packets for the SSH connection to router 1. So before we do that, let's start a capture and let's look at those actual packets, because instead of just visualizing an abstract entity, let's visualize the actual entity that is being sent between the two devices. Before we can do that, let's hopefully get rid of that one single fruit fly going around. Well, it's gone. All right, so let's see here. We've got, okay. So, oh, the capture just never started. I must have hit cancel by accident or something. Oh, either that or it's just plain old not starting. So start, yes, okay, not starting. So this is kind of a new one for me. I guess I'll just try closing it and reopening it. Yeah, last video I got a little bit upset because I was looking at some political stuff, which, as I've mentioned, I don't really want to be a part of this channel at all. And it appeared on the screen when I was changing screens, and I reviewed the video. I don't think it actually did show up, but I did get kind of upset because I thought I had it like tucked away in a different screen. But this is definitely, I'm happy to be part of the channel. This is Heifetz, great violinist. Check them out. Part of the channel. All right, so let's go ahead and yeah. So okay. So now let's see if the Wireshark Capture works. Ah, so it's working now. All right, so we've got ISIS packets over this link because we didn't make this passive interface. So this here you can see is why it's important to make those links passive that go to machines that can't do anything with this, because otherwise look at all this extra traffic you've got, these ISIS, it's cluttering up your capture if you're going to do one, and it just does nothing at all. So making these passive links for protocols where you don't need traffic sent over is really important. But I did not do that. We've also being flooded with DHCP discover messages, which I find really interesting because for some reason it's not able to work. There's a few reasons that could be for that. I guess the most interesting thing for me is that it works on one guest 2, but it doesn't work on guest 1. And there's really, I don't see a big difference in the configuration. But we won't need to look at any of that, so let's filter that out for SSH. And then let's rebuild that connection because we won't have any unless we actually do something. Now we should be getting SSH traffic for that. So I'm thinking it's not showing up under SSH. It might be showing up under TCP. One thing that's important to know about SSH versus Telnet as well is for Telnet, every single last character you send is sent through its own packet. So when you sniff out a password using Telnet, you're going to find multiple packets, and at the end of each packet is going to be the character that was sent. SSH does not do that. It groups together things you send in a different way, and it includes more information per packet than Telnet does. Yep, so this is really interesting to me that it's not capturing it. I think it's because the bug is happening where it stops capturing. Okay, so now we're getting information related to SSH. Yep, so let's filter out for SSH. There we go. So going down here, now you'll see this will start to scroll when I enter commands. Yep, so you see as I enter in commands, enter key and all that, we're getting SSH packets sent, and we're getting responses back. So these are all responses back. So what we want to think about is the SSH traffic that is sent. So, and we want to think about the packet, which is going to be here. This is all going to be the segment, because the segment is encapsulated inside a packet, and the packet is encapsulated inside a frame. So it's important to know which of those, packet, frame, or segment, is interesting when it comes to matching traffic attributes using ACLs or just understanding what is happening in the network. Okay, but we want to focus on the packet, which has the IP addressing in it, and then it has the differentiated services field that will come to the forefront more when we learn about QoS. But here the only thing that really matters is the source and the destination address. So let's see how those pop up in the actual bits. So the source comes first, destination comes second. All right, and you can see the packet starts here. And it starts with the version of the IP, IPv4. Then here, yep. Flags, so we got fragmentation flags, reserve bit, don't fragment, more fragments. Yep. We got our protocol identifiers, this TCP, it could be UDP, or it could be OSPF. OSPF is a protocol as well. There's more protocols than just TCP and UDP. All right, but let's take a look at the source address in the routing table. Right, so we've got it's directly connected. So now let's take a look at the address, the destination address. Okay, so this is directly connected to. So it does make sense that we're not going to need a, that we're not going to lose our connectivity when we stop the IGP, because this source address is directly connected, and this is directly connected as well. But where it would normally be a problem if you're connecting a router to a router, we don't have the same problem because we're connecting the Ubuntu Docker guest to a router, and our Ubuntu Docker guest has this default route on it. So if you were connecting to a router to a router, you would need a similar default route like I have here in order to connect this. So that's why we were having troubles connecting the two, but we're not having the troubles here because we've got the gateway of last resort set up on the Ubuntu Docker guest, and that's all we need to connect to the loopback address, since it is a directly connected route and it wasn't learned. Okay, so that makes sense. It was a bit different than I expected. I thought the connection would have been dropped, but kind of point of this channel is to learn more about networking. Oh, configure delete. Yeah, that's going to work. All right, configure private and then delete. Okay. Okay, and then we'll need to delete it for 8 and 9 as well. All right, so everything seems good. All right, now we'll need to configure OSPF, and hopefully we'll see a number of routes populate. So I kind of lied in last video. I said that 5 routes was too much for me to count up and keep track of manually. I think I can keep track of more than that. So let's make a guess as to how many OSPF routes will show up in router 1 once we've got that configured. So I would say that there are going to be each of the loopback addresses here. So that's 3. And then these are all direct routes, so we're not going to learn those. But these are going to have to be learned dynamically. So now we've got 6. So I would say that we would learn 6 routes by the end of all of it. So place your bets now. Okay, so you'll notice I didn't make 8 and 9 passive. I'm going to go back and do that because we don't need traffic to be advertised over 8 and 9. In fact, the help menu states it better than I could ever state it. It says, do not run OSPF, but advertise it. That's exactly what we want. Okay, so let's see if there's going to be 6 routes learned, and then a 7th route, which is just the multicast route for hello packets. Yep, so we got 6. 1, 2, 3, 4, 5, 6. And as I said, there's 3 loopback addresses, and then there's 3 addresses for each of those links that are not directly connected. All right. The other thing we'll notice is that we've got some on metric 2, and then we've got some on metric 1. The ones that are metric 1 are the loopback addresses. And then a final thing to notice is that all of our interconnect, or sorry, our links, our addresses learned for the links are going to have redundant paths, but our addresses learned for the loopbacks are not. So let's look at that a little bit more deeply. So let's think about router 4's loopback. So it's going to be right here. So the reason there's only one here, and so .4 is going to be connected to router 4 as well, and there's two here, is these are what is known as cost equal paths. To get to this IP address, let's log into router 4 and take a look at it. Okay, so it's directly connected via 001. So let's see which one is 001. Okay, so that's the link to router 2. So okay, so that's this one here. So we can see very clearly this is going to be a cost equal path. You can learn this here. So let's count the steps. Let's count this as 1, and then every device it passes through will add 1 to it, and every link it passes through will add 1 to it as well. So we're starting with 1, with where it is now. It's passing through router 2, so now we're at 2. Passing through this link here, so now we're at 3. So it arrives here with our fake system of computing the costs. We'll look into the real system later. It arrives here with a cost of 3, according to our pretend system. So let's do that going through here. So 1, 2, 3. So it's a cost equal path. Now notice we've got the path here, we've got the path here as well, but we don't have the path here. So let's count that one up. 1, 2, 3, 4, 5. So this is not a valid path because it is not the shortest path to the destination. So it is not included at all. These come up to have the same cost, so they're both included as cost equal paths. All right, so let's do that same exercise for the loopback. So the loopback is configured just within the device. It's not a link. So let's start counting with the device itself, and then we'll start at 1 there, and every time it crosses a link, we'll add 1, and then we won't add 1 for its final destination. So the same strategy. So here we've got 1 for the loopback address. We've got 2 for traversing over this link. And we're just going to keep it at 2 because after it traverses this link, it arrives at its destination on router 1. All right, so let's think about the cost the costs for other paths. So it can also go over to router 3. Then it would be at 1, 2, 3, 4. So you can see there's really no ambiguity for the loopback addresses, which is the shortest path to the destination. So I hope that makes sense. Leave a question in the comments if that needs further clarification. Let's try to look into more detail of the actual costs. Okay, so I think what it is it's the metric here, and that makes sense because these have an additional metric. So if they were starting, if their counting system is going to start at 0, so 0, 1, it's got a metric of 1 for loopback 0. Yep. And 0, 1, 2, metric of 2 for the interface links, but it's got a cost equal path because it's a metric of 2 either going here, 0, 1, 2, or going here, 0, 1, 2. So there's all kinds of ways you can change the metric if you want to, like let's say that this I have a gig link from here to here, and here I only have a fast Ethernet link, but that's going to be important for me because if this link goes down, I want a backup link, but I don't want, well, let's say for the loopback address, I don't want my management traffic to have to be so much slower for my automated config backups and all that stuff. I want that stuff to go pretty quick, so I don't want it to go over this emergency backup link. And now, so you can set the cost of this link higher so that it will only use it if there's no other path. Something I might want to get into, I'll just look at the help menu for that. So I'll do set protocols, OSPF, area 0.0.0.0, interface. Okay, and now there's hopefully something for cost or metric. Nope. Let's see, metric. Interface metric. So I think this is where we can change that. So if we just want it to serve as a backup link and we don't want them to be cost equal paths, even though they are, we can artificially create them. We can artificially assign them in equal costs. Okay, let's see if there's a help for this. And before I do that, I will prove to the world that everything is good to go. Yep, so I can log into router 4, router 3. Oh, it can't run. Oh, yeah, I can run router 3, router 2. Yep, and then I was just in router 1, but I'll need to go in there again because I want to read the documentation on costs for OSPF. So help apropos, OSPF, pipe match, help topic. Oh, that hurt. I bit my lip really hard. I usually don't chew gum, but I've got some special kind that like clean your teeth. Oh, but that really hurt. I gotta pause and come back in a little bit. All right, and I'm back. So we're gonna try to learn more about OSPF costs. So I'm thinking traffic control might be it. Yeah, it's really not straightforward. Let's try traffic control, and if that doesn't work, let's try route preferences. oops. Yeah, this would be this one. So you can control the flow of traffic of packets through the network using route preferences. Route preferences are used to select which route is installed in the forwarding table when several protocols calculate routes to the same destination. The route with the lowest preference value is selected. By default, internal OSPF routes have a preference value of 10, and external OSPF routes, or OSPF routes that were redistributed from a different routing protocol, have a reference value of 150. Although the default settings are appropriate for most environments, you might want to modify the default settings if all of the routing devices in your OSPF network use the default preference values, or if you are planning to migrate from OSPF to a different interior gateway protocol. If all of the devices using the default route preferences use the default route preference values, you can change the route preferences to ensure that the path to a particular device is selected for the forwarding table anytime multiple equal cost paths to a destination exist. When migrating from OSPF to a different IGP, modifying the route preferences allows you to perform the migration in a controlled manner. All right, so that wasn't totally useless. Let's continue looking at some more help documentation. So I actually don't remember what that was. I think it was route preferences. Let's look at traffic control. Oh, but that's for IPv version 6. Okay, so let's look at standards. And then after that, how about traffic control? And then that'll be the last one. Okay, so standards usually just gives you a list of the RFCs that are being used. And I did check in with my coworker. You can't Google an RFC, pull up any documentation you would like. They have preloaded documentation you can look at during the test, and you don't get anything else besides that. But you also get this too, which is why I'm kind of getting used to it. So yep, let's look at traffic control, and that will be it. Once a topology is shared across the network, OSPF uses the topology to route packets between network nodes. Each path between neighbors is assigned a cost based on the throughput, round-trip time, and reliability of the link. The sum of the costs across a particular path between hosts determines the overall cost of the path. Packets are then routed along the shortest path using the shortest path first algorithm. Routes with lower total path metrics are preferred over those with higher path metrics. You can use the following methods to control OSPF traffic. Control the cost of individual OSPF network segments. Dynamically adjust OSPF interface metrics based on bandwidth. Control OSPF route selection. Okay, so this is all you need to know. Cost is based on throughput, round trip time, and reliability. And then the sum of those gives you a metric, and then the metric is the cost essentially. It's just the result of the sum of all of the costs, and lower metrics are preferred over higher metrics. So if we look at our routing table, for these equal cost paths we've got, they're both metric 2, so we can't prefer one or the other. But for these, we've got metric 1, which are preferred. We are going to have more ways to get that. So if we artificially raise the metric on one of these routes, we can see that we will learn it through a different path. Let's try that actually. And to be honest, I'm not even sure how to do that really, which is a good thing because I am learning it. Okay, so here we go. So let's set this metric to 100. Commit that and see what happens to the routing table on router 1 for this route. Okay, so now we can see it just had the metric 101 added to it, but those other paths are still going to be a higher metric because they'd be 102 or 103 or something like that. So it doesn't change the result of these calculations. One thing that would change it though is if I change the metric of the path of an alternate path. So let's set the metric of this link here between router 4 and router 1 to be artificially really high. So let's go ahead and roll back this change on router 4. Okay, and then the metric we want to change is for the link that connects router 1 to router 4, because then it will be, remember our counting system before and how it was pretty similar to what they were using, but they started with 0 and then they added 1 for each leg. So it'll be 0, 1, and then arrive here with a metric of 1. Well, here it will be 0, 1, 2, 3, and arrive here with a metric of 3, which is higher than 1. So it will take this path, unless we artificially change the metric on here. Then it would be 0, 100, and it'll arrive here with 100. So the path here would be preferred because that would only have a metric of 3. So let's change this link to 100 and let's verify that behavior. Oops, so protocols OSPF, area 0, metric 100. Okay, so now we'll see on router 1, it's going to use a different path. It's going to be, I'm not sure which, so let's do a show int description, pipe match, router. So this is interesting because it's now going to have a cost equal path because it could go either 0, 1, 2, 3, and arrive at router 1 with a metric of 3 going through router 3, or it could go 0, 1, 2, 3, and arrive with a metric of 3 through router 2. So we'll have a cost equal path now. Oh. Okay, so this is interesting. It actually arrived with the same metric it arrived before. We actually weren't able to increase the metric on that link. I think all we were able to do was increase the metric on the routes advertised from that link, but not routes traveling through that link. So we should have, not on this device because of course there's a directly connected route that's going to take precedence over the OSPF route because it has a lower administrative distance. But on routers R2, we will see a route with a metric equal to or greater than 100. Okay, so this is interesting too, because I don't see that metric showing up on here. And I think it's because I only have it configured on one side. So it's going to learn it going here. So 0, 1, 2 with a metric of 2 instead of 0, 1, 2. Since I only have it configured on this side, but not on this side, if I did 0, then I would have to go 102, and I get it with a metric of 102. But since it's going through here, it's going to be 0, 1, 2, and it's going to show up with a metric of 2. So let's figure out which route that one is. Okay, so this is 10.0.2.2. So yep, this has a metric of 2 because we only configured that on one side. So it's going to go via router 1 instead of via router 4. So let's do a trace route to it. And now if I do a show route on the first hop, we can see that it is going through this interface. And we can see that is the interface to router 1. So it goes this way. Now let's take away the configuration on router 4 that changed the metric. Okay, and now we'll see that our routing table did not change. Oh, looks like it did change. Well, in any case, now we can see we've got a cost equal path. Aha, yep, and we would have a cost equal path. That makes sense because it was those loopback addresses that did not have a cost equal path. So yep, we've got a cost equal path on these. We changed the metric on this, so this part of the path was no longer cost equal, so we saw we only had this. If we do a trace route now to the same IP, so oops, but we're going to need to do that trace route on a different. Oh no, router 2 is the correct one to do the trace route on. Okay, so it only needed. It could go this way now, so that's a faster way to do it. Because it could take advantage of the directly connected routes on router 4. Okay, I'm not 100% catching on to this, but let's go back to the original goal. And that was to try to change the metric to have the ping from router 1 or yeah, the trace route from router 4 to router 1. So we'll do a trace route 172.16.0.1, source 172.16.0.4. Okay, so we notice it's going to go right there. But if we change the cost on the link to router 1, Okay, now it's going to have to go through a different path. And now it's got a cost equal path because you can either take this one or that one. So that much is definitely true. So let's roll back that configuration change. All right, and I think I might stop the video now. It's been going on for a while. I did not get through, so I set up OSPF throughout the whole topology. I changed it from ISIS, so everything is good to go. There are 6 OSPF routes on router 1. So in the next video, I will be exploring OSPF authentication. Thanks for watching.